Hello everybody, in this video I will be talking about multiplication and division. This will only be a theory video, I won't be making any circuitry. The main reason for that is because we don't need it just yet. Let's start with multiplication, after that we will do division, and let's also talk about squares and square roots while we're at it. Let's say I want to do 5 multiplied by 9. How do we calculate this? Well, there are a few ways we could do this. Actually, two. One is by just adding 5 to itself 9 times. So it will be 5 plus 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 5. And that's incredibly inefficient, in my opinion. We could speed this up by using some shift logic, and I'm going to be showing that off right now. So what we would do is we would multiply 4 by 32, and that will be quite a big number. It will be 8, and then 4 times 30 is 120, so it will be 128. And then we want to do 5 multiplied by 32. However, we're actually doing 50 multiplied by 32, and we just shift it once to the left. So 5 times 32 is going to be 150 plus another 10 is 160, so we just calculate that, and because it's actually 50 instead of a 5, we grab our 1 and we move this 4 and then add another 0, so we just multiply it by 10. And then we add these up. These are called partial products, and if we would do that, it would be 1728. And you can try this on your calculator, it should be correct. Let me check. Yep, it's correct. And we can do the exact same with binary, but instead of multiplying by 10, we multiply by 2, which is just shifting to the left. So let's try that in action, I guess. Okay, so we do 1 multiplied by 5. And hold up, this can either be a 1 or a 0. And 1 multiplied by something is just this thing again, because 1 multiplied by 5 is just a 5. So what we do is we just copy this number over, and then we check for the next digit. Okay, this is a 0, and we have shifted 1 to the left, because we're now checking for this number. This is the same as just shifting this number once to the right, and this one once to the left, and then checking the first bit of this lower number. Now this is a 0, and 0 multiplied by something is nothing. So we add a 0 to 5, and as you can see, we have shifted it 1 over. Now this is also a 0, so we add another 0, and we shifted it again. And now in our final shift, this will be our first bit, and this is a 1. And 1 multiplied by 5 is a 5. So we add it right here. The reason why we put it to the left is because it has shifted 3 times. We tried to add it here, but because 0 times 5 is just 0, we didn't. And we just continued on shifting. So the bottom number every single time gets shifted once to the right, and the top one goes 1 to the left. But before we do the shift, we first check the first bit, and if it's a 1, we add it as a partial product. So now we add this 5 to this right here. And by the way, if we just multiply 5 by 2, it's a 10. If we multiply by 2 again, it's 20, and if we multiply by 2 again, it's 40. So this 5 has to be a 40. And of course, we need to add the zeros behind it as well, because else it doesn't make any sense. So 32 plus 8 is 40, and 40 plus 5 is 45, and 9 times 5 is also 45. Our method seems to work, and it's a lot easier in binary than in decimal, because we only have to check if it's a 1, and we don't even have to do any multiplication anymore, because we're only adding and not actually multiplying. Now let's look into division, which also doesn't do any division, it only uses subtraction. So let's do 25 divided by 5, because it's nice and easy. However, it also works with some floating point numbers, and that will be our second example. So 25 is a 16, an 8, and a 1, so we're going to have 2 zeros in between and a 1. So it's now 1 plus 8 plus 16, that's 25. I'm just going to wrap this around this gray wall, and I'm going to add my 5. Alright, now currently we are using 5 bits to represent our number. However, we're going to be using 8 bits later on. So we just take the length of this number right here, and it's 5, so we're going to have 5 cycles. Keep that in mind. Now first we're going to just be writing it on paper, and after that I will explain how this will work in code. And we start off with this number right here, which is just a 1, and I'm just going to quickly put in our answer spots. This is where the answer will be. And what we want to do is subtract this part right here, only this one, by 5. But why? Well, it's pretty simple. If 1 minus 5 is a positive number, then we just take the sum, put it right here, take all the numbers down, and then continue on with subtracting. However, if it's negative, then just take this one and copy it over, because it was not a positive sum. Then I'm just going to add a 0 here, because we were not able to subtract from it with a positive answer. And I'm also going to add a red dot, just so it makes more sense for us. Then we take down all of the other digits. So the 1, the 0, and all the other stuff next to it. Now we try subtracting 5 from here. So we just go one more to the right, which is the same as just shifting the top number once to the left. Now we try 3 minus 5. However, that's also going to be a negative result. So again, we have a 0, and we continue on with our numbers. So as you can see, every single time we've kept 25. But this time it's different, because now we're trying to do 6 minus 5. And that's a positive 1. So it was a positive. So we add a 1 here. And then we take this result and we just put it right here. Then we copy these again. And we have a 5. Now we try subtracting 5 from 2, which is obviously negative. So it fails. And then we try subtracting 5 from 5. And 5 minus 5 is positive again, because it's a 0, at least in binary. I forgot to put a 0 here from the previous subtraction, but this one is supposed to be a 1 again. And there we go, 25 divided by 5 is 5. And if we count how many shifts there were, or subtractions, there were 1, 2, 3, 4, 5. The same as the length of the bits, and there were also 5 shifts. The one at the top was 1 shift. This one is another 3, 4, 5. 5 shifts. And by the way, this is the remainder. However, you could just carry on with subtracting, and then all of these other parts here will be a 0. So you would just be subtracting endlessly and get many more decimal places. So let's actually try doing that. I'm gonna do 7 divided by 3. We're going to be adding a bunch of zeros to the end. Let's go with 4. So there will be 4 numbers behind the decimal. And the decimal point is just like the dot. So it's 7 points and then your number. And then we're going to put in our 3 over here. Oh, like so. Okay, so first we try subtracting here, which fails, so it's red. And by the way, if you look closely, there isn't actually any point where we say, here's the decimal point. We've just made the number look bigger, even though there's actually decimal point here. So our CPU knows that here starts decimal point. However, technically we have just shifted 7 4 times to the left. And that's all we did. Alright guys, so I've just finished the equation. Well, I didn't actually have enough room. However, the answer is roughly 2 points and then this number right here. You can actually read this by doing 0.5. So this is actually 2 to the power of negative 1. This is 2 to the power of negative 2. So just divide by 2 instead of multiplying by 2. And this just goes on and on and on, which is very annoying to count. This will be 0.0625 plus 0.25 and then plus 2. And that will be our answer. However, you could go on for many more bits if you wanted to. So let me just explain what we did, what I did. So the process was exactly the same. We just did it for, well, more cycles. We just add more cycles. That's the only difference. Now it's pretty cool because here we were able to subtract even though we were past the decimal point, and we got a completely different number, which if we went on for another cycle, then in theory it would be 5 minus 3 and that would be positive, and that's how I got another 1 over there. If I do 7 divided by 3 on the calculator, it will be 2.333333 recurring. And in binary, doesn't always look like it's recurring even though it is. And it's also annoying to write it down in binary because, well, it's only powers of 2. So it's also very difficult to count past the decimal point. So this looks like a 5 and it's just shifted 4 times to the left. So it's 5 divided by 2, divided by 2, divided by 2, divided by 2, which is 0.3125. Well, so you could see it that way, that we just shifted 4 times to the right. And this will be 2.3 if we estimated it in binary with only 4 digits. However, if it were to go on for many more cycles, then we'll be very close to 2.333. However, it won't be exact. there will always be a slight imperfection in the number. Now let's go on to square roots, because those are almost the same as division. By the way, this is called long division. It's just a bunch of subtractions with a few shifts included. Actually rotations, but we will come back to that whenever we're actually making the circuit for it. Alright, so we're going to be taking the square root of 49, which is a 32, a 16, and a 1. So we're going to have a 0 here for 8, a 0 for 4, a 0 for 2, and then a 1 because, well, a 1. First of all, let's make some pairs. So this is going to be a pair, this is going to be a pair. So we have 3 pairs in total. If this was 8-bit instead of 6, then there will be 4 pairs. And the amount of pairs is equal to the amount of cycles that we will have. And this is the long division method, so it's almost exactly the same. Now our divisor, which is just what we are subtracting by, will start off as 0, 1. So we're going to be subtracting from this pair. And this is success. However, since we're taking the square root, the number will always be half the amount of bits. It won't be more than that. So we only need 3 digits to represent the square root. Now because this was a positive answer, 3 minus 1 is 2, we can put a 1 here. And we're actually going to mark this as orange. And the reason why is actually pretty important. So now we're just going to be taking all of these pairs and we're going to put them here again. It's fine to mark them like this if you want. You're only allowed to mark the pairs here because this is no longer a pair, it's just the sum. And now what we're going to be doing is we're going to take this 4-digit number and we're going to subtract the 0, 1 from it. However, we also want to stick our current answer to the left of it. So that's why this was orange, so that we can see the difference. And now we're actually doing 8 minus 5, which is 3. So again, it was a nice positive subtraction. By the way, I'm just gonna mark them. And so it will be 1, 1. A little spoiler alert, the square root of 49 is 7, so all 3 of these should have a 1. Then we take the final pair and we glue these together with the sum. And now we have 13. Then what we're going to be doing is subtracting 0, 1 from this. Once again, we always take a 1 from it, and then with our sum that we currently have. So this is perfect. This is a perfect square root because 13 minus 13 is 0. So our remainder is 0. And the only reason why this is our remainder is because we stop here. If we were to continue, then the square root would become more accurate and more accurate and more accurate. Oh, and by the way, there should be an arrow right here, though they aren't that important. And this will be a 1 because it was a positive subtraction. Yes, 0 is positive in this case. So taking the square root of a number is very close to just long division, except instead of shifting once every single time, we shift twice because, well, we take pairs. And also, the divisor actually gets updated every time that the answer gets updated, which is pretty important and also pretty interesting, because where does this algorithm come from? Well, to be honest, I have no idea, but that's how we take the square root. And by the way, one more thing, getting the square of a number is just multiplying by itself. So we would just do the multiply algorithm where both input A and input B are the same. For example, if I was taking the square of 5, I would just do 5 multiply 5 and that will be done. Now, taking the power of a number is a little different and there are a few algorithms for that. However, this video is getting a little long and it's pretty difficult to explain as well. It requires a lot of abstraction in order to get the result. And I think I'll make a separate video about it, with the machine included. So thank you guys so much for watching and see you in the next video. Make sure to subscribe and like, by the way. And the next video will be about memory. Bye!